Welcome to the Mechanics of Solids lecture series. In this next series of videos, we're solving for peak bending stress, and we'll also look at a beam design problem. The lesson objectives are to be able to compute the normal stress in a beam due to bending at any specified location along the beam and anywhere over the cross-section. And based on this, we should also be able to identify where the maximum stress occurs and calculate it. Finally, this leads to another type of problem, which is to design beams based on strength criteria. The first example is a comprehensive example. We have a simply supported beam with an overhang, constant distributed load, and then we have the channel section and with the cross-section properties given. We're asked to find the peak tensile stress and the peak compressive stress and indicate where on the beam they occur. Because we have an unsymmetric channel section, we should note that the peak tensile stress and the peak compressive stress may not occur on the same location along the beam. Anyway, let's summarize what we need to find. We need to find sigma max, or the maximum tensile stress, sigma min, or the maximum compressive stress, and because we're working with English units, we desire these to be in KSI, stress units in KSI. We're also asked to find the location at which those maximum stresses occur. The approach, in order to be able to find the stress, we need to find the moment over the beam, and we need to, in that case, we need to solve for a shear and bending moment diagram. Once we know where the maximum moment occurs, then we'll use the channel section properties to calculate the stresses. So let's start with a shear and bending moment diagram. I'm going to label the pin support at the left end as support A, at the roller support B, and I want to calculate the reactions A sub y and B sub y at support A and B respectively. I'll start with the sum of the moments about A equal to 0 to solve directly for B sub y. I think this is the best choice because if I sum moments about A, I can handle the distributed load all in one term. So here we go. B sub y times the length or distance from support A, which is equal to 12 feet. That's a positive moment. It's acting in the counterclockwise direction according to my sign convention. Then I'm going to subtract the contribution of the distributed load, and I'll use my shortcut WL squared over 2, where W is equal to 200, L is equal to 18 feet, the length over which it acts. Square that, divide by 2. This total term is in units of pound-feet. Set it equal to 0. Therefore, B sub y is equal to 200 over 2 times 18 squared pound-feet divided by 12 feet, and this computes to 2,700 pounds. Now for A sub y, sum of the forces in y equal to 0. We have A sub y plus B sub y minus the total force, 200 times 18 pounds, that's due to the distributed load. Set that equal to 0. A sub y equals 200 times 18 minus B sub y, 2,700 pounds, or 900 pounds. Okay, so switching to a new slide, I've denoted my reactions, 900 and 2,700 pounds. It supports A and B. I've drawn the lines for my shear force and bending moment diagram and labeled them in the correct units. And now I'll proceed to draw the shear diagram. Starting from the left end, shear jumps up by 900. Because the distributed load is uniform and downward, the shear is going to decrease linearly. It looks something like that. The value at support B I can calculate as 900 minus distributed load 200 times the length over which it acts, and that computes to negative 1,500. So that's my value right here. Then the shear jumps up by the amount of the reaction, so jumps up by 27. The value at the top is negative 1,500 plus 2,700, which is 1,200. And then on the other side of support B, the shear is going to decrease again linearly. And the value at the end, 1,200 minus 200 times 6 equals 0, which is a good check because we know the shear should come back to 0 at the end. I'll use this to compute my moment diagram. Because the shear force is linear everywhere, the moment is going to be quadratic or curved everywhere. Starting from the left end, 0 at the pin support, then it's going to curve up and achieve a maximum where the shear is 0, and those should be lined up on your diagram. Then it's going to continue to curve and come back down. It's going to drop below 0 because this shear area is larger than this shear area. Okay, so based on that, we can compute the value at the maximum and the value at support B. Let's start with the maximum. We need the area of this little triangle on the shear force diagram. First, we need to identify this distance, which I'll call x. Remember the rule, x is equal to the value of the shear at the end, 900, divided by the slope, or the distributed load, 200, and that gives me 4.5 feet. So my moment at the maximum at 4.5 feet is the area of the shear, which is triangle, 1/2 times 900 times 4.5, which is 2025. And I'll denote that value right there where it occurs. Then to get the value at point B, I take 2025 minus the area of this rectangle or triangle on the shear diagram, 1/2 times 1500 times that length, which is going to be 12 minus the x value of 4.5, or 7.5, and that computes to negative 3600. So that's the value of the moment at this location. My diagram isn't quite to scale, but that's okay. And then finally, what happens at the end is the shear is positive and linear, so the moment is going to be quadratic and curved again. It's going to increase, and it's going to increase like this, back to 0 at the end. And I can tell the curvature of the slope because the slope is going to be larger where the shear is larger. The slope is going to go to 0 where the shear is 0. And the value is negative 3600 plus 1/2 area of the triangle. Sorry, I forgot to note the value right there, 1200. 1/2 times 1200 times 6, and that is indeed 0, which is confirmation that it comes back to 0 as we expect. So there's the shear and the moment diagram, which we'll use in the next video to complete the problem.